Okay, this is from a different class. But I still think if I share that, that'll be what we need to do. Okay. So this is from, as I said, a different class, but let me see if I can go back a little bit. I think this was from our, I believe our office hour. Someone asked me to prove the Chapman-Kolmogorov equation, state and prove it. So we did that, I believe, at office hours. And nope, this is something else already. We also did, we did this problem, which was from the sample test. So this was problem 1, I think. We classified the states in this way: 3 and 4 were recurrent, 0, 1, 2, and 5 were transient. And then we figured out the rows. We were asked to find these 3 rows. And we did it using mainly problem 9b, which I think I did in class. And this was sort of an example of how to use it by solving systems of equations. Someone wants to see this more detail, say so. Otherwise, it's more or less a recap. This turned out to be row 05, I guess. These we didn't do, and we'll probably get to this today. And later on, later on, we're able to find row 5, which may have been, that was part of, I'm not sure where that was in the scheme. Any questions on this, going over some of the stuff we did in office hours? Let me forward this. If I can. Yeah, so I'll just build on this if I can. Page. See if I can put lines on this page. And I think we're good to go here. So, well, I guess a reminder, a couple of reminders. We have our first midterm, exam 1. What was it, a week from today? I believe so. October 29th. You have the sample test, I hope, and I think we tentatively agreed to a review session. I believe it was this Friday. Today is the 22nd, so that would be September 24th. And I'm trying to remember, was it like 5 in the afternoon? Is that right? Starting time?
Yeah, I think so.
I think so too, but 5 to 6 or 7, I don't know. So that,
Pretty sure we said 5 to 7.
that's 2 days from today. So here's a reminder. It would be good if you could try to do as many problems as you think you know how or familiar.
Professor, you wrote October instead of September.
I wrote October. But, where did I write October? Over for the for this one. Yeah, thank you. That should be, these both should be September. Thank you. Yeah, especially on that one, because I want to get the right date on the exam. It's not that far away. Okay, it's 1 week away. So that's, thank you again. Okay, so so this will be a Zoom meeting again, the review coming up. And of course, there'll be office hours after today and Friday as well. And as I said last time, in office hours, we did part of problem one. And if there was a state to prove the, yeah, we did part of problem 4A, I guess. So we'll keep chipping away in that way during office hours as well, trying to get ready for this exam, which is a week away. Now there's also a reminder, I guess I never really brought it up, but I believe it's true. Someone could correct me if I'm wrong. I think there's a colloquium today at 1. Can anyone confirm that?
I think there is, but I don't remember at what time.
Yeah, it is at 1.
Yeah, usually it's Wednesdays at 1:50 or something like that. I think, Nellie, I think it was you who told me that there were some pretty good student speakers there, maybe just last week. I'm not sure when. I didn't catch it.
Yeah, it was like a week or two ago.
Okay. And one of them spoke on Markov chains. And this coming time, I think there are 2 other student speakers. So those are usually pretty good sessions. And it's a good way to find out about what students are doing in the department. So that's today at 1 o'clock. I'm sorry I don't have the Zoom link, but I'm fairly sure if you look under math and stat colloquium somewhere, calendar, you should be able to find that if you're interested. Also, I think a topic occurred, not sure, I think it was in office hours concerning my research group. So let me just put that out, take a moment to advertise that. I have a research group which has been going on for many years now. And it's a group of students who want to find out about doing research outside the classroom. So it's not a class, and you can't take it for credit or grade, but you can come to it or join us informally. And everyone is invited. The research group is on 2 topics, one of which people in here are natural, Markov chains. And we're going to get to Markov processes later, but right now, Markov chains is what we're doing in the research group, and it's what we're doing in this class. And the other topic is matrix properties, which has to do with linear algebra. So these are the 2 topics of the research group that I'm overseeing. When it's going normally, it meets roughly once a week, usually for an hour or more, but you're not required to stay any length of time. You can come when you wish, you can leave when you wish. It's very informal. For those who become regulars, there's an opportunity to have some research experience on the side, be involved with a group of myself and a few students that are doing things that are little beyond the class. So you might think, well, gee, I don't know Markov chains that well. I've only been in this class for 5 weeks, and you might not be interested for that reason, but that's probably not the way to think of it. Why? It turns out many of the people in the group haven't had even as much as you have. They haven't had this class in Markov chains. So they picked it up on their own from going to the research group or just filling in the gaps on their own. Same thing for matrix properties. Matrix properties usually People are more comfortable with that if you've had a course or more in linear algebra. And now there's a required course that would be much more than what we do, Math 4190. And so if you've had that, you would be more than qualified to go to this research group. But if you haven't had that, again, that doesn't exclude you from going, and maybe you can just pick up whatever you need from the group. So question is, what's the advantage of doing this activity? And the advantage is, I guess if you come, I think there are advantages any way you take it. If you actually get involved in the group and start coming regularly, there's opportunity for you to take part and to actually engage in some research activities, which is good. It lets you know that there's more to math than what's in the class as well, outside class activities. And if you really get to become a regular, then you can end up contributing by going to mathematical meetings and giving talks. So that's one of the things that the research group does. It usually throughout the year gives about 3 or 4 talks, or 2 or 3 to 4 talks. And your names could be on these talks that are delivered in a mathematical conference setting. And that could be put on a resume, which could help you in a variety of ways. It could help you as far as scholarship and trying to get some support. It could also help you in terms of going to graduate school, if that's something you're interested in. It's also a nice way to get to see mathematics done at conferences, which there are other opportunities for sure, but this is a nice way, and it's an active way because you could be your name could be on a talk that's given. For those who even, are more involved with this, there will eventually be opportunities for you to be the speaker of these talks. So usually as people spend more time in the research group, they work themselves into a position where they're confident and comfortable enough to actually give some of these talks. So I'm happy to have people do that. And that's, again, a good experience to have, and something that you could use on your resume. I'm not the only one doing research groups in the department. There are other faculty members too. They don't all work the same way. Mine is sort of informal. So I have a mailing list. And maybe it's a good time now for me to make more than just, I know there's some people in here who've asked me about getting on this thing. Raymond is one. Sure I'm spelling your name correctly. I think Ricky the other day was another. Millie, I remember, asked me about it too. I'm not sure who else. Was it Hugo? I'm not sure. So these are some students in here who've asked before. Is there anyone else who would like to be on the mailing list? Okay, well, you can pass on it now. And that's fine. And if you have second thoughts, just let me know. I know these were 3 people, I believe, who've asked me. There are already a few people in class who are in this thing. David Beecher, who's in this class, he started doing things in reverse order because he was in the group before he had a class on Markov chains. And he's been in the group for some time now, and been very active in the group. Zach is another person who's attended some of our sessions. Not as involved as far as Beecher in this sense. Beecher's been there over a year, but Zach has also been there. So there are some classmates here that you might want to talk to. They can tell you more. Any questions about this? It's inclusive. So if I haven't mentioned it before, or somehow you've heard me talk to others about it, and you just wondered why you were never invited, here's an invitation. Okay, it's not official. I don't have an announcement to send to you, but it's an invitation now to take part. And again, you can come as much or as little as you want. No one's keeping track of attendance or anything of that sort. Well, except if it becomes obvious who's interested in staying. Okay, that's the end of that ad, and there are other groups in other areas. So if you're into algebra or something else, you might want to ask around. All right, let me get back to the math. Statistics as it is in this class. Let's flip the page. Can I stay on the page? Maybe. So I'd like to develop some more theory that's done in the book. And this is straight out of the book. So let me tell you what I'm talking about now. Some of the things that appear on the sample test that we haven't had time to get to yet. So this starts on page 17 and 18 and 19. And actually the proof of it goes to 20. So I would say pretty much 18 through 20 of the book. So that's what I'm talking about now. So see pages 18 through 20. Not going to do all of it today, but I'll do some of that today. So let's get started. On 17, it talks about what rho is, and it's fine. That's something we have dealt with now a lot. So I'll just say rho xy. I'm going to use their notation here instead of IJ. I think it's, since I'm closely following the book, it's easier to use their notation. And their notation for this is the probability if you start at x that the time it takes to get to y is finite, less than infinity. And well, we've talked about this in different ways. We've talked about how to calculate this. So from the definition, you can calculate this matter. Oh, what does it mean? It means this, t of y, first hitting time is finite. Subscript means that at time 0, you're at x. So x and y are what? Two points in the state space. Okay, so this is what we're doing. And I'll write it as a sum. So the first time you hit y, given that you started at x, could be in 1 unit of time. Or it could be in 2 units of time. So that would mean 4, since it's either 1 or 2. And the sum goes on forever. So I'll just do one more term and then use 3 dots. So this is saying that if you start at state 0, let's say x, it should be. So we're assuming that at time 0, you're at state x. And the time the first hit the time the first hit y is 1 unit of time. The time the first hit y is hit y for the first time is 2 units of time. The time the first hit y is 3 units of time, and so forth. So we've seen this already. This is a long infinite series generally, and if you can sum this infinite series, that's equal to what's going on here. Okay, and our interpretation of this has been, this is the probability of eventually getting from x to y. Probability of eventually getting the eventually is saying all the times when you can do it. You can do it in 1 time, 2 units of time, 3 units of time, and so forth. Okay. Uh, what I want to get to is on the next page, so I'm going to flip the page. They have a notation that looks a little familiar to something that I'm doing in my other class. So for the few people who are in both classes, here's a chance to double down on the concept. They define on page 18, or the top of it, they define this thing. One y, z. And this is called there the indicator function of the set y. So indicator function of set y. And they tell you how it's defined. So this is the name, indicator function. And they tell you it's a very simple function, by the way. It looks like this. It only has two values. And in this scheme, y and z are things in the state space. Y and z are states. And this function is equal to 0 if, right in slightly different order than they have, if y and z are not the same state, and it's equal to 1 if y and z are the same. So if you think of these as two states in the state space, y and z, the indicator function is 1 if the two states are the same. And it's 0 if they're not the same. So what does it indicate? It indicates whether you've got two states that are the same or they're different. And it only takes two values, 0 and 1. Now, for people who are in my other class, and there's like 2 or 3 of them, we have the same kind of function there with a different notation. There it would be denoted as capital I of YZ. And that's pretty good too. I mean, this capital I there refers to the word indicator. And 1 here, in a sense, indicates, well, what are the values of this function? It's either 0 or 1. Normally, you're interested when it's 1, because when 1 happens and something interesting happens, the two states are the same. And if they're not the same, that's not quite as interesting. So a good way to think of this thing is an on-off function. So like a light switch in your house is either on or off, and hopefully if the light bulb is working, if it's on, you're able to see have less darkness. And if the light bulb either doesn't work or it's in the off position, then they're not, they don't have, it indicates whether it's something is on or off. So whenever you have something that takes two values, if you want to call those values on and off, or working or not working, whatever words you want to use, that's when the indicator function sort of comes into play. Okay, I'll try in this class to follow your book's notation, which is this. Now, where is it coming up? It's coming up in the context here of a Markov chain. So remember, we might as well assume, explicit, assume we have a Markov chain. And we've done enough examples of those to know what they look like. And we also know that they come with a collection of random variables, x0, x1, x2, and so forth, in general, xn. And this could be regarded as the various states you are at time n. So here the index is time. And time, in this case, is the natural numbers. It's going up like, well, natural numbers plus 0, perhaps 1, 2, 3, etc. Okay. So to make the connection with Markov chains, and this over here is the definition of the indicator function. So I'll just write it as DEF. Any questions before we make this connection between the two ideas? Okay. So let's scroll down a little more. They say, well, they're interested in a new random variable. So let's define n of y. Capital N of y. And how we define this to be the number of times. This is the number of times and the times, we'll call those n, sort of like these things. But the number of times that are positive, we're not counting where we are at 0, that the chain is in state y. Markov chain is in state y. So we've already said that we're looking at where we are for different points in time. And if the state y, well, what could happen? It could happen, for example, maybe at time 2, you're at state 5. I'll just write that as equal. And maybe at time 7, you're back at state 5. And maybe at time 16, you're at 5. And that's it. So you're at state 5 at these times, at time 2, at time 7, and at time 16. And you can imagine there to be the usual diagram with, going from one state to the other. And you find yourself at state 5, being at state 5 at these 3 times, and no more, and no other times. Other times. Okay. So if that happens, then the number of times that you're at 5 would be 3. Because this is 1 time, this is the 2nd time, this is the 3rd time. And because you're not at 5 at any of the other times, you're only at 5 3 times. So capital N is counting how many what? How many times you're at this state. And by the way, that may vary, right? I mean, in this case, you could visit state 5 3 times. Maybe if you did it again, maybe you'd be at state 5 6 times or something like that, because it is a random situation. You're going from one state to the other. So for example, if you had simple suppose you have this kind of a simple Markov chain that looks like this. But whatever these are, so suppose this is 1/2, and this is 1/2, and this is 1. The number of times you're at 0, well, it could be that it's counting the number of positive times. It could be that you go from 0 to 1 immediately. And if that's true, the number of positive times you're at 0 could be 0. That would correspond just to going from 0 to 1 on your first step. On the other hand, maybe you looped here a few times. Now, let me see. Well, actually, no. Oh, by the way, this is wrong. Okay, the number of times you're at 0 is that, right? So suppose you looped here a few times. You could have looped twice. So you could loop and then go up. In that case, the number of times that you're at 0 would have been number of positive times you're at 0 would have been 2. Because you were here at time 1, and you were here at time 2, and then you went up to time 3. So you actually were at state 0 2 times. So I'm explaining what capital N is in terms of this. What would be the number of times you're at state 1? Well, you could say that depends. That depends on how many times you loop and where you start. If you start at 0, how many times you'll be at 1 would depend upon how many loops you make here. But however many times you loop, you get at 1. Once you're at 1, you're there all the time after. So this could actually be infinite.
Professor, I have a question.
Sure.
For your example, loop going up, wouldn't
Right.
it be 0 because we have to, or do we not count for the initial state?
So I'm doing this assuming I'm starting at 0. So if I start at 0, then the number of positive times I'm back. So what do I know? I know at time 0, I'm at 0. And then I'm saying at time 1, I'm still at 0. Why? Because I looped. And then at time 2, I looped again, and so I'm still at 0. So when I say loop up, I really mean stay here the first unit of time, stay here the second unit of time, and then finally go over here. So let me see, at time 2, I would still be here, but then at time 3, I would be at 1. So if this happens, then what I'm looking at is how many positive times was I at 0? Well, there was this positive time and this positive time. So that would be this. Do you see what I'm saying?
Yeah, sorry, I didn't read that it n has to be greater than 1. My bad.
Oh, that's fine. That's easy. Yeah, you could. That's a natural thing to do, by the way. Is you might want to start the times at 0, but this starts the times at 1 or beyond. Okay, so it's not a hard, but it's a random variable, right? Because the number of times, you can see from this, the number of times that you visit 0 basically depends upon second here. Got somebody coming to my front door. Okay, hang on one sec. Let me see if I can see something that needs to be answered. Yeah, there's my doorbell. I'll be right back. That's pretty funny. Did you guys hear any of that stuff?
I didn't.
He's not.
Okay, so
No,
guy came to the door. He wants to do some gardening for me. And I don't know him, but anyway, there's a little bit of negotiations and he's going to do something. So that's cool. Okay, but I'm sorry for the interruption. Completely unplanned, completely random. There, I guess I could relate it to the class that way, right? What's the probability someone would come to my door and try to sell me something? But in this case, it all worked out, I think. Sorry for the interruption. Where was I? We were doing capital N. Oh, and I was saying it was random. And you can see it's random because the number of times you actually visit 0 in this case depends upon how many loops you make, right? And so it could be this. So what's the point? Capital N of Y, or in this case, capital N of 0 is a random variable. And actually, let's make sure that's clear. So I'm just going to stick, this is probably the simplest example I can come up with, right? So if it's a random variable, what are the values it takes? Well, it's possible the number of times you visit 0, the number of positive times, because that's how this thing is defined, right? Number of times greater than or equal to 1. It could just be once. Well, it could be 0. You could never, there, you can leave here at time 1 and never be there. So there's no positive time you're there. And it could be 1 and it could be 2. And it could be as many times as you loop, right? So how many values are on here? An infinite number. What are the probabilities? Yeah, it's not X, it's N. So this is the number of times we are at 0. That's what this means. So the number of times that you're at 0, let's call that little n, say. What's the chance that you're here? Not at all. Well, that would be the chance that you leave immediately, which would be 1/2. What's the chance that you're at 0 only once? Well, that would be the probability of looping and then leaving. So that would be 1/2 times 1/2. What's the chance that you visit 0 exactly 2 times? Now, this is very simple because once you leave, you can't come back. If it were more complicated, then I'd have a more complicated calculation to do. But I'm not trying to be complicated, and I'm trying to give you the simplest example that I can think of and yet show you the randomness. So if you want to visit 0 twice, you would have to do what I already said. You would have to loop twice and then go up. And once you go up, you never get back. So that would be looping twice. That's 1/2 times 1/2, and then going this way would be an 1/8. And so it would go, right? And in general, if you wanted to visit 0 n times, it would be 1/2 to the what? Well, when n is 1, this was 1/2 to the 2. So I guess it's 1/2 to this. Let's make sure that agrees with all of these. When n is 0, it would be 1/2 to the first, which is this. When n is 1, it would be 1/2 to the second, which is this. And yeah, that's like the pattern. Okay, so what's the point? The point is the number of times you visit a state. And remember, it's the positive number of times. Or no, I should say, right, the times that are positive that you visit a state, you're not counting 0. So the positive times that you visit a state could be a random variable, which means what? You could, it has a table like this. You can find its expected value. You can find its standard deviation. You can do everything that you do with normal random variables. Okay, any questions about what NY means and how it's thought of as a random variable? it seems like a natural thing to think about, right? Because when you have a diagram and you're moving around the diagram, it seems like the number of times that you visit a state could come up. In fact, and by the way, what could be on the list? This thing could stop at some point, or it could go on. Both possibilities are there, right? So you might have a situation where you visit a state only so many times, and then that's it. Or you might be able to visit, as many times as you want. Okay. Any questions on what NY means? We haven't talked about it before, so this is a new time. Now what? Now, oh, well, they write NY in the following way. So NY, the number of times that you visit state Y, can be represented in terms of these indicator functions. So you add up the indicator function of little y of xn. And you sum from n equal 1 to infinity. Okay, so why? why is this equal to this? And what does it really mean? It really means, so when you put in a summation notation, it's always a little more intimidating than it really is. It really is saying that this is 1 y x1 plus 1 y x2, etc. Okay. And now we can start to see what's going on. So let me go back to one that I made up over here. So suppose we had this situation. So here, this is a little more complicated than this example. But here I'm just giving you information. What have I given you? I've given you the 3 times we are at 5 and no other times. Okay, so I'm assuming we're at a Markov chain. And at these times 2, 7, and 16, we are at state 5. Okay, so, and at no other times is that true. So what would this thing say now if I put in, so assume that, assume this is what's going on. Assume we're at 5 at these 3 times and no other times. Okay, so let's verify that this equation is correct. The number of times that you're at state 5 would just be 3, right? Because the positive times that you were at 5 were 2, 7, and 16. Okay, so we know what this thing is. Now, what would this give us? This thing would give us the following. The state that we're at is 5. So we put in what the state is now, it becomes more meaningful. So that would be that first indicator random variable. This would be the second indicator random variable. And this would be the third indicator random variable. That's a 1. And it says indicator, so plus, this keeps going. Okay, now this thing, what is the value of this? Well, it's an indicator, so it's either 0 or 1. It's like an on-off switch. I already said that. When is it equal to 1? It equals 1. This equals 1 if what? X1 is equal to 5. If this equals that, then it's 1. And if this does not equal that, then it's 0. Okay, and I probably should have put the time. Well, okay. Yeah, that's fine. Okay, now at time 1, are we equal to 5? No. Because I already told you, the only times you're equal to 5 are these 3 times and no other times. So this is not true. At time 1, you're not equal to 5. which means this value won't be 1, it'll be what? 0. It can only be two values, 0 or 1, because it's 1 if this equals that, and it's 0 otherwise. That's how it's defined. And I've already told you the only time you're at 5 are the times of what? 2, 7, and 16. So at time 1, you're not at 5, so that means this is a 0. What about the next one? At time 2, are you equal to 5? Yeah, you are. So that one's a 1. What about the next one? At time 3, are you equal to 5? No, because I told you the only times you're equal to 5 are these and no other times. So the next one's going to be 0. And so it will continue when, let's go up to 7, which is the next time. So what I'm saying is 1, 2, 3, 4, I'd be 0. 5, I'd be 0. 6, I'd be 0. But 7, I'll be 1. Because this is the indicator function of 5x x3. And we were told from the beginning that x7 3 there. Yes, but that 3 will become a 7. So when you get you're up to the 7th term here, then you're going to get a 1. So what's going on? This sum will only be 1 when you are at the state in question at that time. So in this case, it happened at time 2. It's time 2. It happened at time 7. It'll happen one more time where at 16, there'll be a 1. And at all other times, the sum will have terms that look like these, zeros. So this is going to be adding up to 3 by adding up 3 ones that occur as the 2nd term, the 7th term, and the 16th term. That explains why this equation holds in general. Does it make sense? It's knee notation. So if you're a little off balance with it, well, I hope this example makes some sense of it. I mean, each of these are the real simple guys, because the indicator functions are just two values. They're 0 and 1. So if you want to think of it as a random variable, they only take two values. But what we're saying is the total number of times you're at the state Y can be represented as the sum of indicator functions over as time moves forward. So it's a summation over time. And all this is a bunch of things that look like either zeros or ones. And when it's 1, that's the kind of thing you're counting on the left side. When it's 0, then you're not counting you're trying to count all the times you're at state Y. And in this case, state 5. And there were only 3 times. There could have been more, right? But there were only 3. Okay. So this is important. Next thing he says is this set. When this occurs, is the same as when this occurs. So these are 2 different events described in 2 different random variables. We already know what this one means because we've already dealt with this. This is the first hitting time. And this says the first hitting time is finite. So the first hitting time is finite. Which means, the first hitting time could be 1, could be 2, but it could be a finite number. What is this saying? This is saying the number of times you visit Y is greater than or equal to 1. what you have to convince yourself is that these two sets are equal. How do you show two sets are equal? So I'll just, and by the way, at first glance, they're defined in different ways, so it doesn't look obvious. But how you show two sets are equal, if you're trying to show that A equals B, what you typically show is what? That A is a subset of B, and then what else? B is a subset of A. That's how, from math 3100, you try to show that two sets are equal to each other. Okay, so let's assume we're in here. If we're in here, what does it say? It says the number of times we visit Y is greater than or equal to 1. The number of positive times we visit Y, really? Because that's what this was. So the number of positive times, positive times you visit Y is greater than or equal to 1. It is the number of times you visit Y is greater than or equal to 1. Okay, now I don't know where we started, but it doesn't matter here. This is just looking at times your Y, where the time you're there is 1. So let's pretend that we started somewhere. Call it X. If there's a time that we visit Y, that means X of n equals Y, where n could either be 1, 2, or something like this, or 3. So if the number of times you visit Y is 1 or more, there must be a positive time, which means it's not 0, but it's either 1, 2, 3, where you're equal to Y. Okay, so if you're in here, you definitely visit Y at some positive time. And I'm saying that this is saying the time that you first visit Y, well, I don't know what it is, but I know I will be visiting Y because I'm in here. I visit Y at least once, 1 or more. So that means this also occurs. The time that I first hit Y will be some finite number, whatever number it was down here. So there's some n that makes this true. If you pick the first n that makes that true, then you'll have the time that you first hit Y in n steps will be less than infinity. So that means if this happens, then this happens. That's all I'm trying to argue. If I actually visit Y for either n equal 1, 2, 3, or something, then there's a first time that I visit Y. That's finite. So what I've shown or argued there is this conclusion, that if this happens, then this happens. What's left to convince ourselves is that the opposite is true. Suppose you're in here. If you're in here, what we already said, that the time you first hit Y, it could be, the time you first hit Y could be 1. At the time you first hit Y could be 2. At the time you first hit Y could be 3. It could be any of those. So if you're in here, there's one of these is true. Either the time you first hit Y is time 1 or 2 or 3 or etc. One of these is true. Why? Because that's what this says. The time it takes to first hit Y is finite, which means it has to be either time 1 or 2 or 3 or something like that. Okay, so suppose, just for argument, suppose the time it first it takes me to hit Y is 10. So suppose this isn't true, and this isn't true, and this isn't true. None of them are true until I get to time 10. And that's the time I first hit Y. Okay, so that's something in here. But if I first hit Y at time 10, then the number of times I hit Y would be at least 1, because I hit it at time 10, right? It might be more. I might hit it again and again. Who knows? But if there's a first time, and that's what being here means, if there's a first time that you hit y, a first positive time, like that first positive time could be 10, then clearly the number of times you visited y is at least once, because you visited at time 10, and you might visit more. So, but who cares about the more? If you're in here, then you're in here, and that completes sort of the proof. I didn't write much. And it's a little slippery. You might have to put it in your own words. But have I given you some idea why these two sets are the same? Let me see if I can put it in everyday English as a summary. If the number of times I visit y is positive, then there has to be a first time that I visit y, and that first time will be a finite number. I think that makes sense if you think of it that way. You're in here, which means the number of times you visit y is positive, one or more. Then there has to be a first time where it occurs, and that first time will be a finite number. That gives you this inclusion. On the other hand, if the time it takes you to first visit y is a finite number, like 10, then it's clear you visited y at least one time, because you visited it time 10 and maybe more. So if this is finite, then the number of times you actually visit that state will be 1 or bigger. So it's not a hard thing, but it is a set equality. Okay. So now, so let's put this with that. So these are sort of proofs, but they turn out to be somewhat useful things too. So far I have two box equations. I have an expression for ny in terms of indicator variables. And we have an expression relating this set to this guy. So this is relating ty, the first time you hit y, with ny, the number of times you actually visit y. There's a relationship in this manner. Then they say, so here's a consequence of this. A note. Suppose you start at state X and you're interested in hitting Y at least one time. Maybe more. So if you start at X and you want to know the probability that you visit Y at least once, that's the same as starting at X. And since this set here, greater than or equal to 1, is equal to this set here, we can replace this condition with the condition that ty is what? Less than infinity. What am I doing? What's in the parentheses here? We already said that event, whenever that happens, is equivalent to this event. So I can replace it with this event. But this event is one we already know. This is what we define to be rho xy, which is what? The probability of getting from X to Y eventually. So now if you read from far left to far right, what do we got? We got this. If you start at state X, the number of times that you visit Y is greater than or equal to 1 is equal to rho xy. Another useful formula. Questions on that one? Okay, I see I'm almost out of time. Really, I'm out of time. Let me see if I can do one more thing. What we want to do next is sort of the next step of this. So remember, this is assuming you start at time 0 at state X, the number of times you visit Y is 1 or more is this. What if we change the 1 here to 2? So I'll try to squeeze this in. What are we trying to find now? You started, we're in a Markov chain, you started at state X, And you want to know the probability that the number of times you visit state Y is 2 or bigger. We already know how to do it when this is a 1. So we're asking, how do we do it when there's a 2? And here's the argument the book gives. I'll say it, maybe I'll say more after class. But here's what they say. So I'll just, for simplicity, lift what they're saying. They're saying this is a double sum where n is going from 1 to infinity, and where n is doing the same. And what are you summing? You're summing the probability that at time x, the time it takes the first hit y is m, times the probability that starting at y, the time it takes first hit y from there, first positive time, is n. Okay, well, let's think about what's going on here. Here's the timeline. At time 0, so here's the timeline. At time 0, here's time. And underneath it, I'll put the state you're at. So at time 0, you're at state x. This thing is saying the number of times you visit y is at least twice. So there has to be the first time you visit y. Let's call it, what do I want to call it? How about time 1? The first time I visit y is here. And in between here, we didn't visit y. And then the next time I visit y is here. And I know there's at least 2 such times because of this. The number of times we visit y is 2 or more. So there's at least 2 such times. There could be more. You could have visited more than twice, but at least you visited this many times. So here's how things look. At time 0, you're at this state. There'll be a time when you first get to y. And then there'll be another time when you return to y. And I know that's true because that's what's going on here. And now what he's saying is, how could the picture look like this? Well, the first time he's actually calling m in this index. So he's calling this m. And the second time you visit y, he's calling, well, is it that right? Yeah, that's right. And then the second time he's calling that n. And so that follows from this. You're visiting y at least twice. So there has to be a first time and there has to be a second time. And this one could be any of m, and this could be any of n, and that's what he's doing here. He's saying, and I can write it a little more, I can write a little more. This thing in here, he's saying is really, if you started with x, you want the first time you visit y to be m, and you want the second time you visit y to be n. And that's what really he wants in here, because you know there's at least 2 times you visited y. But the question becomes, how does this turn into that? And the answer is, what does all this really mean? It really means that this really means this. Conditioned upon where you were initially, which was at x. Okay, that's what this notation means. So knowing that you started at x, what's the chance that you first hit y at m and then you did it again at n? So here I'm assuming that n is what? Greater than n. But if I were to write this out, it would mean what? It would mean probability of this and this and this divided by what? Divided by the condition. So I'm giving a little more detail here than it's in the book. The book just goes from here to here, and I'm trying to explain how we're getting this thing in here. So I'm saying that what should be in there are all the ways you could start at X and you could first hit Y at M and then hit Y next at N. And that's a conditional probability that looks like that. And by the definition of conditional probability, it looks like that. And now what? On top, you've got three conditions. So write it as the first condition, this one. Times the second condition, given the first, times what? The probability of the third condition, given the first two. T Y. Okay. And keep what's on the bottom the same. We've done this a number of times. This is the probability of this event and this event and this event. So this is the multiplication rule. The probability of the first event, probability of the second event given the first event, probability of the third event given the first two. Okay, but this cancels this. So that takes care of that stuff. And this, that's just the probability of going from X to Y for the first time in units. So that's this thing. So the second term here is just the same as starting at X and ending up at Y in units of time. Now the second one here is the more interesting one. You know where you were initially, you know where you were after n units of time, and you want to know being here in n units of time later. But being Markov chain, this doesn't matter. You can cross that off by the Markov property. And saying that you were first at Y in time n means what? Means at time 0, you were not at Y. Well, you know you were at X, so that's true. You're not at Y. At time 1, you're not at Y. At time 2, you're not at Y. And then what's the last condition? You were first at Y at time n. So at time n, you were back at Y. So the condition here has a lot of information. It tells you where you were initially at time 0. Well, we crossed that out. But if the first time you were at Y is M, then you weren't at Y anywhere else until the end. You can cross off all this information by the Markov property. It's the distance passed. So what does this turn into? It turns into knowing that at time n you were at Y. Right this way, you know where you were at time n, and from there on, the time it takes right. Yeah, the time it takes the first to hit Y, essentially the second time would be that n. And that's what they're doing in the book when they write it like this. Okay, well, speaking of time, I'm basically out of time, but it turns out the last step, you can now sum sum this part over here. We turn this double sum into a sum over n, which involves this part. And the remaining sum over n involves the other part. I'm almost hesitant to write it, but I will. So the sum over n involves this, the sum over n involves that. And if you look at that, what you get is just this. This one is starting at x, the chance that you get to y in n units of time, but n could be anything. So that turns out to be rho xy. So now I'm up here. I've justified where we're here. And here, this first summation over m is rho xy. And the second summation over y, over n rather, is rho. Let me see if I got it right. Rho yy, yeah. Because here, summing over n, you're assuming you're at y because you've already reached there the first time, and then you want to, from there, go to y again in n units of time. So this is sort of the second part of the journey. So bottom line, what's the bottom line? The bottom line is this stuff here equals this. So write it and then call it a day. So the probability starting at x, the number of times you visit y is 2 or more, is equal to this. And I went through the details of this because it's useful, but now that you have it, it's easy to interpret. So if you start at x and you want to visit y at least twice, you have to get from x to y the first time. And it may take a long time. So that's the probability of going from x to y eventually. So the first term, in this first factor here, is you can think of it as the chance of getting from x to y for the first time. Well, okay, once that occurs, now you're at y and you want to get back to y again. Why? Because you're visiting y twice. So that would be the probability of getting from y back to itself. So that's the interpretation. Let me stop because I'm way over time. I don't think there's any new homework to give you. I mean, we have the outstanding homework already of the sample test. So let me just take a water break and come back and work problems on the sample test or answer any questions from what I did today. We didn't get real far, but it's a good start. So I'll see you in about 15 seconds. Okay. So let's talk about office hours. Since the screen is still here, I got a little rushed on doing this. And should I go over this again, or do you have any questions on this whole panel? Actually, this panel, I have to compliment my tablet for a change. OneNote, it let me do the whole class on one sheet here. So hey, that's pretty cool. So I can quickly ask, is there anything on this one sheet which goes on for a while that you need clarification on? We did a lot. We talked about the indicator random function, and the indicator function and the indicator variable, and the number of times we visit a state, what it means. We've got this way of writing in. So things in the box are sort of important. This equals this. We actually went through that little demonstration. And that led to what? Conditional probabilities of both of them led to this conclusion that if you start at x, the number of times you visit y being bigger or equal to 1 is just rho xy. And then we tried to do this replacing 1 by 2. And just without going through the details, the answer turned out to be this. Here's a nice thing to do next. What would be the probability? So we just figured out this. The next order of business could be, we start at X. What's the probability the number of times we visit Y is 3 or more? So what am I pushing? I'm pushing. We already did 1 or more. That was this thing here. That turned out just to be this, because these two sets were the same. And then we just did chance of visiting Y twice or more, worked out to be this. So if you want to see the pattern, if you're going, what I hope you would get away from, what the takeaway might be from the previous one would be this. You're starting at state at time 0, you're starting at state X. There'll be some time where you hit Y the first time. And then there'll be a time when you hit Y again. And there'll be a time where you hit Y a 3rd time. They don't have to be evenly spaced. But this is saying starting at X, you're going to visit Y at least 3 times. And with this picture, what we would guess this to be now would be, what's the chance of getting from X to Y eventually? That's rho X, Y. Once you're here, everything in the past is sort of forgotten. What's the chance of going from Y to Y eventually? That's rho Y, Y. Once you're here, everything that's past is forgotten because it's a Markov chain. What's the chance of getting from Y to here again? That's another rho Y, Y. Okay. When you don't prove things, you can get real far fast. I'm not proving it, but I'm giving you some justification along the way, an explanation. If you start at X and you're going to reach Y at least 3 times, suppose you do it 3 times, getting from here to here would be this. I don't know how long it's going to take me. It could take me a long time to first visit Y, or it can happen quickly. It could be anything. It's random. But the probability of eventually getting from X to Y is rho X, Y. Once I'm here, I need to come back again because I'm visiting Y 3 times. So the whole thing restarts here. And chance of going from here to here eventually is this. So I'm here, the whole thing restarts again. The past doesn't matter because I know where I am. I'm here. And I want another chance of visiting Y once again. That's this. If you want to generalize this, this should now become fairly clear. If you're at X, you want the number of times that you visit Y to be greater than or equal to something. Let me use their notation. Find it. They do M. So what does it mean? The picture is this. At time 0, you know, where you started at X. Some later time, you find yourself at Y. And then sometime thereafter, you find yourself at Y again, and again, and again, and again. And the times between visits could be very random until this last time. And that would be visiting, that would be the nth time. Nth time we visit Y. And if we're just trying to gain intuition and remember a formula, how it works would be, well, you got to get from X to Y eventually. And then you have to get from this y back to itself. And then from this y back to itself. And keep going. How many little YYs do you have? Well, if there were, we already saw, if there were a visit of 3 times, then there were two of these factors. So if there's a visit of n time, there will be n minus 1 of these factors. So what will this thing become? This whole thing will become rho xy times what? Rho yy to the n minus 1. So if you want the bottom line, start at x and you want to visit y at least n times. The way to calculate that would be rho xy times rho yy to the n. And if you visit only once, then this term disappears and you just have rho xy, which is one of our first ones. Okay. So we're gaining a lot more information about the probability of visiting y and so many times. Questions on any of this stuff? So here's a question. Is this on the sample test? It is, but not yet. It's close to the case. Okay, so this is sample. If you look on sample test problem 1, the one that's closest to this that we could almost do is now this one. So that appears on sample test problem 1C. 1C has 3 questions, and this is just one of those. It's close to this, but not exactly the same. So what we could do is this, and what we've done just now in class, the chance, if you start at 1, that the number of times you visit 5 is greater than or equal to 3. That would be this. So it would be rho xy times rho yy to this to n minus 1. That would be this. So if you were trying to find, if they'd asked us this from what we just did in class and after class here, this would be the answer. But now the question is, we don't want greater than or equal, we want it to be equal. And a way to think of that would be this. Find the probability that the number of times you visit 5 is greater than or equal to 3. Right. Yeah, do a picture. I think it's going to be this. Greater than, okay, so I'll write this down, but I might have to modify it. This is saying the probability that you visit 5 4 more times. And then you take away the chance of visiting 5 3 or more times. That would just leave you the probability of visiting 5 4 times. So since I don't want that, I want this one. Uh, 3 in here and 2 in here. why do I want this? Well, this would be all the ways you could visit 5 3 or more times. And this would be all the ways you could visit 5 2 or more times. So visiting 5, say 4 times occurs in here and it occurs in here. Because visiting 4 times, it makes both of these conditions true. And visiting 3 times, it's both true. Let me see. Think about this. Maybe I was right to begin with. So here, all the ways you can visit this 4 times or more, visit this 3 times or more. But everything in here is also in here. But if you subtract this, that, I think you just get equal. Which is what you've been asked to find. Okay, so if you're in here, you visit 5 4 or more times. If you're in here, you visit 5 3 or more times. But visiting 5, say 4 times or more is in here, 4 times or more is in here, 5 times or more is in here, and in here, 6 times or more is in both of them. So when you subtract, those get canceled. So the only thing that doesn't get canceled is when you visit 5 3 times, which would occur in here, if that doesn't occur over here. So maybe I have to do the reverse. Yeah, I think I have to do the reverse of this. I think it has to be this. I'm just thinking out loud. Okay, so which set is bigger? This set is bigger. Because if you visit 5 3 or more times, that includes 3 4 5 6, all those number of times. If you visit 5 4 or more times, that includes just 4 5 6 7. That's it. So everything in here is a subset of this. So this set is bigger than that. So if you take this set minus that, you'll get the right thing. Okay. And both of these we now know how to do. So I'm going to do this again in class next time, so don't get too worried about it. but to finish it off, this one we just said already from class that if you're going to visit 5 3 or more times, you have to get there once. And I guess in this case, where we're going is 5. And where we're starting is 1. So in this particular case, we're going from 1 to 5, and then we're going from 5 backwards from 5 2 times. So if we wanted this, it would be equal to this in this problem. And then what I just had here before I lost it. And 5 was what? Greater than or equal to 4. And that one would be row 1 5, row 5 5 to the third. So when you take the difference, you get this. Row 1 5, row 5 5 to the second power times what? 1 minus 1 5. Let me say why this makes sense. This is the probability of getting from 1 to 5 eventually. Think of that as the first step of the journey. Then you want to go from 5 to 5 2 times in a row so that you visit 5 3 times altogether. This is the first time, and these are the second and third times. Okay. However, in this case, you don't want to visit 5 any more times because you don't want it to be greater than or equal to 5. You want it to be equal to 5. So the chance of visiting 5 a fourth time is this, and 1 minus that is the complement. So this corresponds to the probability of not visiting 5 again. So that would be the answer on the test. If you wanted the chance that you actually visited 5 exactly 3 times, figure out the chance of getting there eventually once, coming back twice, and then never visit again. Okay, but we couldn't do it without what I just went through over here. So this should be the answer of the sample test problem C, the middle problem. Row 5, 5, I think we did last time. So the only thing left to talk about is 1C. Is the expected value of 1 and 5. And I can either do that next time or now, but I'm not sure what you want to see, so I'll just throw this up into request. Maybe you have other problems on the sample test you want to see. Maybe some sample test comes to mind. Homework problems come to mind. Clarification.
Professor, I was actually wanted to know if I could run my answer for homework problem 17 by you.
Homework problem 17, sure.
It's
You
to show that if X leads to Y and Y leads to X, that they communicate.
Got it. Yeah, so let's flip the page. I'm pushing my luck on this, I think. Okay, so I'm going to get a new page. I'm still impressed that I had the whole class on one page today. That's new ground. Where am I? That's where I'm at. No. Okay. So I've just succeeded in getting lost. Give me a second. Yeah, that's today's. Okay, so I want to add a page to this. I want to some lines on it. Okay, so I can't see my lines. I don't think I've got my lines. Huh. I don't know what happened to my lines, but I'm not going to worry about it. Okay, so you want to run through homework problem, what, 17?
Yeah.
So let me just make sure. I think it was to show. Well, let me just actually look at it to make sure I got it the way they want it. So page 43, 17. Show that if X leads to Y, X leads to Y, and what else? Y leads to Z. Then what? X leads to Z. Sure. What's your idea?
So I just used equation 28 basically. Right, if X leads to Y, then there's some time N or N1 I used that, you know, it reaches Y. And then from there, you would reach Z at some other time, N2. And then based on that, X leads to Z.
I think you're okay. You're using 28. I might use, let me see. So what's our definition of X leads to Y though? That's sort of key. So I think I said there exists an N such that what? Such that P X to Y N is positive? Does that look familiar?
Yeah, you've used that in the past before.
Yeah, if I use that, so I think I would go with that. But then, okay, so maybe, okay, so I think I'm using your idea, but I'm probably filling in a detail or two. So I'm using this. And then that's using this. Then what is this? We get to assume both of these, right? So Y leads to Z means, let's say there exists some integer, these are integers, such that what? Such that, you know what? For reasons that will become clear real soon, I'm going to call this one an M. And then I'll call this one an N. Some other integer N. Such that what? Pn of YZ is positive. Okay. So that's what we know. And what we'd like to show is that there is a way to get from X to Z. And I think you were going to use equation 28. I would probably use something that comes to mind. For me, I would use the Chapman-Kolmogorov equation. Because what does that say? And then I'll get back to what you're saying in a minute. That says if you want to go from X to Z in time n plus n, you can do it by first going from X to Y in time m, and then go from where? Y to Z in time n, and sum up over all the places that you were in between. Okay. So this is a Chapman-Kolmogorov equation. Actually, we did it in class and it came up the other day in the office hour. So this sort of nice. So it says here it's telling you how to get the chance of going from X to Z, where you've gone through some intermediate point. So what I'm thinking is, if you've got this thing being positive for some m, and this thing being positive for some n. So if you know that there are particular values here, yeah. So suppose you pick the m and n so that there would appear here in Chapman-Kolmogorov. This thing here will be bigger than Pm xy times Pn yz. Why will this sum be bigger? Because because these things are probabilities. And here you're summing up. Let me see if I'm doing this right. Yeah, and okay, so it's a little confusing. Y is some intermediate state in this Chapman-Kolmogorov, but in what we're doing, Y is just the place you're going to on the way to get to Z, right? So Y is an intermediate state, and I'm saying that this product would be bigger than this if you just pick one of the terms. Why? Because everything is not negative here. And if you drop off the other terms for different y's, you're just leaving off positive stuff. And now these are each positive. So the product of two positive things is still positive. And now you're done. You've shown that there's an integer so that going from x to z has a positive value. Okay, so I probably would use Chapman-Kolmogorov. So before I get back to what you did, does this make some sense?
Yeah, actually, I think that's like a simpler way of what I was trying to do.
Yeah, I think so too, because I think the equations that you were using sort of come after Chapman-Kolmogorov. I think.
Yeah,
So the idea though is you get to assume that there's an m that makes this positive. So there's a positive probability going from x to y in m steps. And there's a positive probability of going from y to z in n steps. And you're trying to show there's a positive probability of going from here to here in some integer number of steps. And yeah, I'm using the Chapman-Kolmogorov equation to say, well, that's sort of what it gives me. It tells me the chance of going from the first state to the last state in this much time. So all I have to do is argue that there's an m and n that makes this positive. But that since there was an m and an n that made this positive, I don't have to add up all the other terms. I can just look at the terms that made this positive, and that makes this positive. It sort of completes the idea. So I think it's probably more or less what you're doing, just maybe like you said, a little simpler. So maybe I'll quit it right here if that's okay with you.
yeah, that's fine. Thank you.
You're very welcome. Other questions?
I have a question. Could you go back to the page you were working on before going to 17?
Sure, at least in theory. Let's see. Yes, it works out. Okay, but where do you want to be on this page? It's very long.
Was at the very bottom, I think.
Okay. Because I even talked after class, so I don't know. Let me know when I get to your.
Was that boxed equation right there? Where n5 is greater than or equal to 3 right there?
Yeah, yeah.
Wouldn't that expression on the right side be more fit to be equal to the equation above it? Because from how I'm understanding it is you go from x to y once, and then y to y a second time, and the third time. So wouldn't that be exactly
This.
hitting it 3 times? Yeah.
Great question. Great question. Thank you. The answer is no, but it's a great question. So let me tell you why. This is going from x to y once. This is going from y back to itself 2 times, right? So when you've done all this, you've gone to y 3 times. Once initially from x, and then 2 more times. Somewhere I have a timeline written out here. I don't know where it is. Oh, here it is. I think this is sort of it. Yeah, this is even better. So you're figuring out the probability of going from here to here, and then from here to here, and from here to here. If you stop it there, you have visited y 3 times, but there's more time here, right? In order to get this far, you've just made use of the time it takes to go to here, to here, to here. And when you stop it there, you really don't say what goes on afterwards. It's conceivable that you come back to y again.
Mhm.
And if you don't want to come back to y again, which is what's going on here, why don't you want to come back to y again? Because the number of times you visited, 5 is just 3 times. It's not more than 3. It's exactly 3. So that means what you really want to do is make these 3 visits and then never come back. and never come back is where that last term comes in.
Oh, okay. Right, because
Okay.
that's the complement of going back to it again.
Yes, yes, yes. But it's very reasonable. What you thought is a very reasonable thought, because it looks like you've met the condition, and indeed you have. You have visited 5 3 times. But there's another little condition that you don't want to visit it any more than 3 times.
Mhm.
So this ensures that you don't get back.
Okay, yeah, that makes a lot of sense.
Good. Anyone else have any other questions? Have you gotten any further on the sample test? Let me let me see what I think you can do now. I'm beginning to think you can do well. Okay. Pardon me. What you can't do yet, and I actually don't like to even put it that way. What I haven't covered yet, because who knows, maybe you've read ahead or something. I haven't covered the stuff in problem 6. I hope to do that, at least start it next time. So number 6 would be probably not something not to concentrate on yet. 5B, I think we did. 5A is where we're going. So 5B, 5A, the stuff we did today leads to 5A. So I think I'll finish that on Friday. So, but it's still a little out in front of us. I think most of what's left is fair game. So if there's anything here that you tried, or even if you haven't tried, and you're just curious how it works, feel free to request it. And I understand if you want to look at it first and ask it on Friday or something, that's fine. But if you had any questions, there's time now too, so it's up to you. Did I talk about 3 on the sample test?
I don't think so.
I don't think so either. Did anyone try 3 yet? I mean, if you,
I personally haven't.
Yeah, me neither.
why don't I play with it a little bit just to get you into it? And then we'll see if we want to do more. But again, if you had something that you did try and you want to ask, that takes preference. If you don't, I'll just look at 3. Okay. So let's get a clean sheet. So where are we? This we just did. And maybe one more after this would be fine. Good. And I'll see if I can get my lines. Yay, I got them. Okay. So 3 reads as this: suppose you have 3 red balls and 3 white balls evenly distributed between the 2 containers. And I'm thinking maybe this is a homework problem for us. I don't know. Let's go a little further. Let the number of red balls in container 1 be the state, and at each unit mix the balls as follows. Randomly pick a ball from container 1 and place it in 2. Then randomly pick a ball from container 2 and place it into 1. Okay, now I'm trying to remember if we did a problem like that. So let me look and see. It looks to me like one of the early homework problems. So let me double check that. So the one that it reminds me of a little bit is problem 2 on page 41. We have 2 boxes, 2 D balls. Some are black, some are red, and here what is going on. Red and white, but that's not a big difference. Okay, I think this is problem 2 on page 41. Now that's all fine if you did problem 2. So what I think I'll be content at, well, okay, 2 things. One, I'm alerting you that I think this is problem 2 on page 41, which means I think we've done it as homework. So and you might want to go back and look at that. But regardless of that, let me do at least part A of it. So part A, looking on 2 on the, well, 3 on the sample test. Part A. So so it's talking about states being 0, 1, 2, or 3. And what are the states? Let's see. It says, let the number of red balls in container 1 be the state. So you got these 2 containers. And there are 3 balls in each of them. And apparently there'll always be 3 balls in each of them. Why? Because if you read the description, how does the mixing occur? At each unit of time, mix the balls as follows. Pick a ball from 1 and 2. So pick a ball from 1 and place it into 2. Then pick a ball from 2 and place it into 1. Ah, that's different than what I just said on problem 2. Problem 2, okay, from the homework, has you pick the balls simultaneously from container 1 and 2 and just switch them. Okay, that's problem 2 from homework. This has a subtle difference. You're not picking balls simultaneously from both containers. See what it says. It says, at each unit of time, mix the balls as follows. Randomly pick a ball from 1 and place it into 2. Then pick a ball from container 2 and place it into 1. So you're putting 1 ball from here into here, which means there'll be 4 here. Then randomly pick one of them and put it into there. So it's conceivable you could have the same distribution of balls as you had initially. Okay, so for this problem, you really have to concentrate on how the balls are being mixed. And they're being mixed by picking one from here, randomly putting it into here, and then picking randomly one of the balls from here and putting it back in the original. let me make sure I read it right, but I think that's what it's saying. Randomly pick a ball from container 1, place it into container 2, then pick a ball from container 2 and place it into 1. The number of red balls in container 1 is the new state. Okay, okay. So now let me get the diagram so you can at least get some idea of this. So let's suppose we're at state 0. So, well, let's see. And the balls are of 2 colors. So what does the state represent? The state represents the number of red balls in box 1. So there's 3 red and there's what, 3 white. Okay. And the state is how many red balls is the number of red balls in box 1. Okay. So if we're here, the number of red ball, there will always be 3 balls in box 1 because you're switching one out and switching one back in. So there'll always be 3 balls, but the state is the number of red balls in here. And this is saying, suppose the number of red balls is 0. So if that's what it looks like, then it looks like this. White ball number 1 is in here, white ball number 2 is in here, white ball number 3 is in here. And over here sits the 3 red balls. Red ball 1, red ball 2, red ball 3. So if needed, label the balls so you can tell them apart. Okay, so initially here, there's none in here. None what? None, no red balls. What can happen? Well, let's think about what could happen. You're first picking the ball from container 1. And it'll either, well, in theory, it'll either be red or white. In this case, it's got to be white because the only thing in there is white. So this is certain and this is 0. And then you throw that ball, the white ball, into here. And you randomly pick one of those and it's either red or white. So let's call this the first pick. And this would be red or white, the second pick. Okay, if you had no red balls here, then you would have introduced a red ball into here. And the chance of picking, I'm sorry, if you have no red balls here, then you would have introduced a white ball into this container. And the chance of picking a red ball from that container would be 3 out of 4. Whereas the chance of, again, randomly picking the ball that you just put in there would be 1 out of 4. On the other hand, if the ball, no. Oh, I see. I don't even have to do that because I can't get a red ball from this. Okay, but if so this is more what can actually happen. You get a white ball from this, throw it in here. The chance of getting a red ball would be still 3 out of 4. And this would be 1/4. And I'm trying to see if I did this, if I even want to say more about this. What I would say about this is don't even do the second half. Because the chance of getting a red ball initially from this is 0. So you don't, the analysis doesn't make any sense. So if you're at 0, you've got to get a white, you've got to be moving a white ball you've got to be picking a white ball, putting it into the second container, and then choosing again from there and putting something back. So what is the probability that you actually, when you're done, have one red ball in container one? That would be 1 times 3/4, which would be 3/4. So the chance of going from 0 to 1 would be 3/4. And the chance of going from none back to none would be 1/4. Okay, that's a start in terms of getting the diagram, which is problem 3A. You see what I'm doing? I'm assuming that there were no red balls in here to begin with, and then I made a tree. And the chance that I end up with a red ball in here was 3/4. And the chance that I still have no red balls is only 1 out of 4. Okay, now let's go the next step up. The next step up, suppose we have 1 red ball in here. So I don't think it matters which one it is. Why don't we just pretend that red ball 1 is in here. And where red ball 1 now would be what white ball 2. Okay, so I'm assuming that I have 1 red ball in container 1. I'm going to go through the same process. I'm going to pick something from here, put it into here, then randomly pick something from here and throw it back into here. Okay, so it's going to be a tree again, but my initial starting point is now at 1, because I have 1 red ball in container 1. So now I have a little more a tree that is a little more meaningful. I either pick a red or a white on the first pick. And I pick a red or a white on the second pick. Capital W and capital W refer to color, not the particular ball, okay? So, all right, if I pick something from here, what's the chance it's a red ball? Well, there's only 1 in 3 in there. So that's 1 in 3. What's the chance it's a white ball? That would be 2 in 3. If it were the red ball that you chose and you put it into here, now you'd have 3 red balls in this container plus the 1 white ball that was there already. So if you're picking randomly from this, the chance of getting a red would be what, 3 out of 4? Everyone see why? Because you added a red ball to this. And the chance of picking out the one with the only white ball would be 1 out of 4. On the other hand, if you chose one of the 2 white balls and put it into here, the chance of getting a red from this would be what, 2 out of 4, which is a half. And the chance of getting a white ball would also be 2 out of 4, which is a half. So this is how the tree looks if the original container has 1 red ball. Okay, now, what happens? In this case, okay, in this case, we removed a red ball and put a red ball back. So in this case, we'd be coming back to having 1 red ball in container 1. So we'd be at state, we'd still be at state 1, right? Because you moved a red ball for a red ball. And it's similar here, if you remove a white ball for another white ball, and you originally had one red ball in here, you're still back to state 1. But what happens in these two other cases? Here you moved a red and replaced it by a white. So now you're at state 0. And here you removed a white and replaced it by a red. And so now you're at state 2. Remembering that you're starting off with 1 in box, in container 1. Okay, so this is sort of important. Here you just switch 2 balls, but they're both red. So you originally had 1 in here, you still have 1 in here. If you go down this path, you're switching 2 white balls for each other. So you still have only 1 red in here. So you're still at the same state. Whereas at these paths, here you're switching a red ball out and getting a white ball in. So now you have no red balls in box 1. And in this case, you're switching a white ball out and bringing a red ball in. And so now you have 2 red balls. So all of these things would help us get different portions of the diagram. So going from excuse me, well, maybe the easier ones are going, this one gets you down to 0. So the probability that you go from state 1 to 0 would be this times this, which appears to be a 12. So from 1 to 0 looks like a 12. Yeah. Now, how about going from 1 to 2? 1 to 2 happens if you go down this path. The probability of that occurring is a half times 2/3, so that's just 1/3. So to go up is 1/3. And what's left? Well, what's left is going from 1 to 1. There's 2 ways to do it. You can forget the tree if you want and just use the diagram, because 1 out of 12 times you go down, 3 out of 12 times you go up. So that means 4 out of 12 times you either go down or go up, which means 8 out of 12 times you stay pat, which means you're staying here, which is 2/3. Not 2/3. Try that again. 1/3 is 4/12. And this is 5/12. So this would be what, 7/12? Okay, I'm just getting that by realizing that all these probabilities have to add up to 1. But let's go back and use the tree just to make sure. So if you're going to go from 0 back, from 1 back to itself, you either go on the top road, which would be this times this, which would be the chance of traveling down this path would be 1 out of 4, just by taking the product of these 2. And the chance of going from back to 1 here would be this way, which would be 1/3. And so either could happen. So it would be 1/3 plus 1/4. And this would be everything in 12ths. So this would be what? 4/12, 3/12. It would be 7/12. And I don't know, is that what I got before? Yeah. 7/12. Okay, so I'm like half done with this thing. Why am I going over this? If you can't do 3A, problem 3 is a skip for you. Okay, so getting the diagram is important because all the other parts depend on it, I think. Yeah, I'm pretty sure. So I'm half done with the diagram. I think it's probably symmetric, but I don't know. I don't know. But before I worry about the rest of it, any questions about the part I did? it sort of relies upon the stuff you would have had in an introductory probability course because we're using these trees. I mean, could you do it without the trees, perhaps? We use rules, I guess. The probability trees sort of capture the rules in the picture. Well, okay. Why don't we do 3 back to 3 or something like that, just to see how that goes, see if it is. So if you wanted to go 3 to 3, you would have 3 red balls in here. And you'd have to pick one of those red balls to put in here. And then the chance of picking that red ball would be 3 out of 4, right? So if you had 3 red balls in this thing to begin with, then it doesn't matter which one you pick, you're going to get a red ball and put it in the second container. And then the chance of getting a red ball from here, which means you would end up having 3 back in here, would be 3 out of 4. So it's not symmetric. Let me see if I did that right. I'm thinking this is 3 out of 4, but I didn't write much down, so let me do it a little more detailed. So the details would be this. You're in container 1, and you have 3 red balls. Red 1, red 2, and red 3. And therefore, all the white ones are in here. You pick one of these and move it over here. So you either get a red the first pick or you get a white. But if they're all red, this has to happen. So this is the only part of the tree that's functional. And then you get a red or a white second pick. So if you put one of the red ones in here, the chance of getting another red or getting that same red actually would be 1 out of 4. The chance that you actually get a white would be 3 out of 4. And this has 0 probability of happening if they're all red in here. So the only part of the tree that you're worried about is shown. So going from red back to red would leave you with 3, and that's 1/4. So somehow I got 3/4 before, so maybe it's good to write things down. Let me see if I'm doing that right. Yeah, because if I want to go from red to red and I have 3 in here, then I'll still have 3 in there. And that only happens if I pick out the red ball that I introduced and bring it back. Okay, and then if that's 3/4, well, if that's 1/4, then this has to be 3/4. Okay, so my initial impulse, which was maybe this diagram is symmetric, is looking better. So what would that mean if we buy that assumption? The chance, well, might as well do it. We've gone this far. So the one that remains is we have 2 red balls in here. So maybe we have red ball 1 and red ball 2, perhaps, and white ball 1. And over here, we would have red 3, and white 2, and white 3. Okay. And we're at state 2, because we got 2 red balls in here. And what are we doing? We're picking, and we'll either get a red ball and a white ball on our first pick. Chance of getting a red ball from this would be 2 out of 3. Chance of getting white out of this would be 1 out of 3. switch it out and pick again. So if you switch out, if you pick the red ball and you put it in here, the chance of getting another red ball from this would be 2 out of 4. The chance of getting a white one would be 2 out of 4. On the other hand, if you pick the white ball and put it in here, then the chance of getting a red would be 1 out of 4. And the chance of getting a white one would be 3 out of 4. Okay. So if we switch a red for a red, we're back to where we started. So that would be going back to state 2.